Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First of all, allow me to thank you for the time given to me. My name is Lety Trisnaliani, and I am from Sriwijaya University. On this occasion, I will present a paper entitled Effect on the Variation of Irradiation Time and Power of UVC Lamp on Photocatalyst Degradation of Iron Sulfate Dye Waste. First, I'd like to talk about the introduction. Textile industry wastewater contains several heavy metals, such as ferric iron in liquid ferric sulfate. Light energy is a driver for many biogeochemical element cycles in aquatic systems. The sunlight-induced photochemical reduction of ferric iron to ferrous iron by either direct ligand to metal charge transfer or by photochemically produced radicals can be an essential source of dissolved ferrous in aqueous and sedimentary environments. Therefore, ferric iron photoreduction may not only control the primary productivity in the oceans, but has a tremendous impact on iron cycling in the littoral zones of freshwater and marine environments. And the technology that we have used in this research is a photocatalyst. As we know that photocatalyst is energy saving, and can be initiated by UV lamp and PCB lamp. It is also relatively cheap, sustainable, and environmentally friendly. Based on the research that we have described, the object of the study is aimed to determine the effect of variation in irradiation time and UVC lamp power on the degradation of iron sulfate dye waste with help of photocatalyst TiO2 silver zeolite nanocomposite. The next is methodology research. The first work that we have did is synthesis of titanium dioxide and silver. The synthesis of TiO2 silver was carried out by reacting TiO2 and silver nitrate with aqueous. Then the mixture was stirred for 3 hours until homogeneous. The solution was several times and filtered. Next, the filter solution was dried in an oven for 12 hours to remove the moisture content. The dry samples were then cooked in a furnace at a temperature of 400 degrees Celsius for 5 hours. And the second work is a prepare of TiO2, silver, and zeolite. The feed was stirred for 6 hours at a temperature of 80 degrees Celsius. The solution was then washed several times and then dried in an oven for 12 hours. After the treatment, the samples were cooked in a furnace for 6 hours and at temperature of 600 degrees Celsius. The solid composite dried at 100 degrees Celsius for 12 hours. Changed color to pale pink, namely the color change to pale pink proves that silver precursor has been successfully reduced and deposited on the surface of TiO2 because silver at the nanoparticle size would be purplish pink. The next work is photocatalytic activity test. The nanocomposite of TiO2 silver zeolite was added to 100 milliliter of ferric sulfate waste solution. The mixture was allowed to stand for 30 minutes in a photoreactor. Then the solution was irradiated and stirred at a speed of 50 RPM at a temperature of 30 degrees Celsius for 30 minutes. Determination of photocatalytic activity by taking 3 milliliter of the solution every 10 minutes for 1 hour. Then the concentration was measured as a function of time. And then the determination of optimum degradation time. The photocatalytic test for the degradation of iron sulfate with TiO2 silver zeolite was carried out with 3 variations of UVC lamp, namely 6H and 10 watt. TiO2 silver zeolite as much as the desired variations was added to 100 milliliter of iron sulfate solution with a concentration of 20 ppm. The solution was stirred for 1 hour in the dark. Then 3 ml of iron sulfate was taken. After that, the photodegradation reaction was carried out with a UVC lamp while still being stirred, and 3 milliliter samples were taken. 6 samples were centrifuged at 7,000 RPM for 10 minutes. Furthermore, the solution was analyzed with a UVP spectrophotometer to measure its absorbance and determine the concentration and degradation produced to determine the most optimal composition for degradation using TiO2, silver, and zeolite. As you can see here from the experimental data, using the effect of time, it can be seen in figure 1 that there was no decrease in the pH value of the iron sulfate base. It showed that at pH value with UV radiations, 6, 8, and 10 watt increase. The highest pH value was produced in H watt at 60-minute contact time at pH 4.6. And in this figure 2 shows that the result of photocatalyst activity with UPC lamp irradiations 6, 8, and 10 watt, it produced the highest percentage of degradations in waste iron sulfate with UPC 6 watt at 60 minutes. The degradation process of iron sulfate waste has increased until it reaches the highest at 60 minutes, thus proving that the photodegradation process occurs over time. And the last figure, it is shown that a UPC lamp with a power of 6 watt at 60 minutes result in a decrease in the concentration of 6.79 ppm than an iron reduction sulfate concentration in a UPC lamp with a power of 8 watt at 60 minutes was 8.47 ppm, and at 10 watt at 60 minutes produce a concentration of iron sulfate of 7.17 ppm. And then based on our research, we can conclude that UPC lamp power effects of TiO2 doped with silver metal sensitizer by increasing photocatalytic activity, which can be seen from the increase in the pH value of iron sulfate. Time variation affect increasing the pH value by showing that the longer the time given, the pH of iron sulfate also increase. The power of the UPC lamp, which shows photocatalyst result with a suitable pH value, is an 8 watt UPC lamp with a pH value is a 4.6 at 60 minutes, where ferrous ions appear when the pH is more than 4, and it is produced the highest percentage of degradation of about 51% at the UPC lamp power of 6 watt at 60 minutes. And a pH value of more than 4. This also proves that the photodegradation process occurs over time. Ladies and gentlemen, and this is will bring us to the end of my presentation. I sincerely appreciate your time and thank you. Wassalamualaikum warahmatullahi wabarakatuh.